Hello everyone. In this video, we will talk about setting a hypothesis test for variances of normal populations. So the first topic is we assume we have a population of items in this population that you want to test if its variance is larger than a certain value, and let's call it V0, or less, and sigma 0 square could be 10, 3, 4, or equal. So these are the three possible null hypotheses. And an example, you may want to purchase resistors of 100 ohm. So you went to this manufacturer who produce maybe millions of resistors every day, and you want the variance for the resistors to be within 2 ohms. So if you buy 20 resistors, the value should not go above 102 or below 98. So how do we test if the variance is less than 2%? So this would be the first topic. Now the second topic is test a null hypothesis that compare the variance of two populations. So now we have two populations, and I want to compare the variance of this population with the variance of this population. So there are three possible null hypothesis tests. The first one is I want to test if the variance of the first population larger than the variance of the second population, or maybe less than the second population, or maybe they are equal. So these are the two topics. Now here, the test is possible if the probability distribution of the populations are normal. And to carry out this test, we will need the chi-square and the F distribution. In previous video, I talked about the chi-square distribution. And in this video, I will still review it and introduce the F distribution, which depends on the chi-square distribution. So let's start with the chi-square distribution. First, let's talk about the standard normal population. So that means the mean is 0 and the variance and the standard deviation equals 1. Now, if I take a sample of size n and I create a new variable, which is the sum of the square of the values in these samples, x1 square plus x2 square plus x3 square, and so forth. Now, this random variable will have a chi-square distribution. Now, let's look to the more general situation where the population is a normal population, but it's not a standard. That means it has a mean, mu x, and it has a variance, sigma x. Now, I can make this normal population as a standard normal population by carrying out this transformation. So every items in this sample minus the mean of the population divided by the standard deviation of the population. And if I square it, now these also will have a chi-square distribution. Let's clean up. Now we are concerned about setting a null hypothesis for the variance. And because we don't know the variance of the population, we usually take a sample. And then we estimate this variance by finding the variance of the sample space here. So the sample variance, we learned it earlier in previous chapters. This is the definition. Now, if I multiply this by n minus 1, and I divide each item here by sigma x, now this quantity here equal exactly this quantity, because these will cancel these, and then you will get this one, which is exactly this. So what we did here, all we did is we multiplied s of x squared by n minus 1, which is this, and divide by the variance here, sigma x to the power of 2, that's the variance. So since this quantity is exactly this quantity, now this also will have a chi-square distribution. The only variable here is the sample variance. Sigma x here, it will be a constant, and n here will be a constant. Let's clean up. So that's what we said earlier. We'll have a chi-square distribution. Let's just call it u of k, where k here is the degree of freedom equal n minus 1. And if we plot the chi-square density function, it will look something like this, depending on the degree of freedom. And the equation that describes the probability density function is this one. And when we calculate the probability that the random variable u of k, or here we call it x, equals certain value or less, we are not going to carry out the integration. We're going to use the table, or there is a software that can give you the exact probability. But one thing I want you to pay attention to is the following. The mean of the random variable y of k is k, which is the degree of freedom. And let's take the degree of freedom 4 here, which is this blue one. So the mean will be around 4, which is somewhere here. And the larger is the degree of freedom, the more the density function will look like a normal distribution. Okay, with this review of the chi-square distribution, let's move on now. How do we set a null hypothesis to test if the variance of a normal population is equal or smaller than a certain value, or even larger, depending on the application? Okay, let's start talking about setting the hypothesis for the variance of a normal population. So the problem is as follows. We have a population and it has a variance that we are interested on. So the question now is, the company may claim the variance is larger than specific value, sigma naught squared, or maybe small or equal. So how do we set the hypothesis test to accept it or reject it? So there are 3 possible null hypotheses. The first one is the variance of the population is equal or smaller than sigma 0 squared. And sigma 0 squared here is just like a specific value or constant. The second possible null hypothesis is the variance of the population is equal or larger. And the third one is the variance of the population equal sigma 0 squared. So these are the 3 possible null hypotheses. Which one we will choose, we will see. It depends on the application and the evidence of the sample. So the first step we need to do is to take a sample from this population of size n. So we have here x1, x2, all the way to xn. So let's assume n is 15. The larger the sample, the better conclusion you will reach. The next step is to calculate the variance of the sample, just to get some idea about the variance of the population. The next step then is to calculate the test statistic. So it will be, for this case, x degree of freedom v equal n minus 1, so that's 14. Now, how do we set the null hypothesis? Which of these 3 do we choose? Well, usually the null hypothesis will go against the evidence collected from the sample or the claim of the company. So let's assume the variance of the sample came larger than this claimed number. And usually the company will claim also that the variance or the variation of their product is larger than this sigma squared. And the sample usually will support this claim. So now our null hypothesis will go against the sample and the claim. So my null hypothesis will be H0, the variance of the population actually equal or less than sigma square naught. So how do I verify if the null hypothesis is correct, or should I reject it and accept the claim and the evidence of the sample? Well, we will calculate the test statistic. If the sample variance larger than sigma naught square, as the sample is showing here and as the claim of the company saying, then this quantity will be larger than 1 time n minus 1. N minus 1, this is the mean of the variable, the chi-square. So if I plot the chi-square probability density function for a degree of freedom v equal n minus 1, in this case n 15, so that will be 14, because this skew to the right, so the mean probably will come to the right of the peak. Now, if this ratio larger than 1, then the chi-square variable will come somewhere here. So now the question is the following. What is the probability that the random variable will have a large value, larger than the mean, coming from a population that agree with the null hypothesis? See, according to the null hypothesis, the variance divided by sigma naught square is less than 1. So according to the hypothesis, this chi-square should be somewhere here, but the sample came actually to the right. So if I advocate for the null hypothesis, I may say, oh, this came by coincidence. Well, let's calculate this probability. This is the p-value. If that p-value came 5% or less, then that by coincidence or probability is very, very slim. And the chi-square variable, to have a value larger than the mean, cannot come from a population with variance less than this sigma naught square. And we have to reject the null hypothesis. So basically, larger x square or chi-square provide strong evidence against the null hypothesis, which is this one. Let me clean up. So let's take another scenario. The sample variance came less than sigma naught square. And let's assume the company was claiming that the variation on their product is less than this value. So then my null hypothesis in this case will go against the evidence and the claim. So I will say, no, the variance of the population actually is equal or larger than sigma 0 square. And when I calculate the test statistic, now since the variance of the sample came less than sigma 0, so this ratio will be less than 1. And this is 14, so this will have less than the value 14. So let's draw the probability density function of the chi-square, and the mean is here, that is 14. Remember, the mean of the chi-square is just n minus 1, or the degree of freedom v, which is n minus 1. So now in this case, this quantity, if the variance of the sample less than sigma, will be less than 40, so it may be here. So since I am advocating for the null hypothesis, I may say the sample here gave you a variance less than this by a coincidence. It should be actually larger than 14. So let's calculate what is the probability that this sample will have this value from a population. According to the null hypothesis, its variance larger than this. So that means I need to calculate this p-value. And again, if this p-value came less than 5%, then there is a strong evidence to reject the null hypothesis. The chance of this variable to be less than the mean coming from a population with variance larger than sigma 0 square is very, very slim. So I have to reject the null hypothesis and accept the alternative hypothesis, which is the variance of the population actually is less than sigma 0 square. So smaller test statistic or chi-square variable provide strong evidence against this null hypothesis. The third possible set for the null hypothesis is when the variance of the population equals a specific value. In this case, again, we calculate this. Now, this value if it came 1, probably this is true. But usually it may come larger or less. So if I draw the PDF, the probability density function, and this is 14, so this ratio may be larger than 1, so it may comes here, or less than 1. Less than 1 times 14, it may comes here. So whatever, if it came here, then I calculate this p-value and multiply by 2, and that's the p-value, because I am counting also this. If the chi-square variable came here, then I calculate this p-value and multiply it by 2 to reject this null hypothesis or not. Okay, let's take an example to demonstrate these steps. To check the reliability of a scale in a butcher shop, test weight known to weight 400 grams was weighted 16 times. So we have here the population, you can think of it, is the weights of a standard mass of 400 grams given by this scale. So sometimes this will give you 401, sometimes 398, 99, and so forth. So we want to know the reliability of this scale. For the scale to be considered reliable, the variance of repeated measurement must be less than 1 gram. So we want this variance to be 1 gram or less. The sample variance of 16 measured weight was 0.81. So we used the scale and we made 16 measurement, and the variance of the samples came to be 0.81. Assume that the measured weights are independent and follow a normal distribution. That means all this value here, x1, x2, all the way to x16, don't affect each other. Just because x1 came to be 400, that doesn't mean x2 will be less or more. It could be any randomness. Can we conclude that the population variance of the measurement is less than 1? So can we conclude that the variance here of the population is less than 1? That's what we want to verify. If it came less than 1, that means the scale is reliable and we can use it. If it came more than 1, then that means the scale needs calibration. Well, since the evidence shows it's less than this, then the null hypothesis will be as follows. We will oppose the evidence and say that the variance of the population is equal or larger than 1. The scale needs calibration. And just because the sample variance came 0.81, it's just by chance. So now we have to verify. Did it come by chance, or did it come 0.81 because the scale is really calibrated and reliable? So that's what we need to do. So the first step, we have to calculate the statistic value, which is of degree of freedom 16 minus 1 is 15 equal n minus 1. So if we do this one, that would be 12.15. So 12.15, if this is the chi-square density function for a degree of freedom k equal 15, the value here, 12.15, will be somewhere here. So now we need to calculate this area. If this area came less than 5%, then S square had this value not by coincidence, but because the variance is really less than 1. And we reject the null hypothesis. So we will go to the table and look for this area. This is the table we will be using, and degree of freedom 15, that's this one. And let's look for 12.15 in the table. If we go down, I don't have 12.15, I have only 8 and 22. So if I go 8.547, this quantity, which is here, then alpha is 0.9. That means this area, all this area is 0.9. So this area here is 10% or 0.1. So the p-value is already larger than 10%. So this area, if I use a calculator or a computer, this area will come definitely more than 10%. So the p-value is definitely larger than 0.1, and here is 22 will be somewhere here. And if this is like 0.1, then this will be 0.9 and less than 0.9. Since the p-value is larger than 10%, there is no strong evidence to reject the null hypothesis, which means the variance of measurement by this scale is not less than 1, and the scale need to be calibrated. Bottom line, we cannot conclude that the scale is reliable. All right, the next topic will be test for equality of variance setup. In this case, let's say we have two populations now, and population X and population Y. And you can think of these, maybe here there is speech strategy for cochlear implant, and the mean of speech perception is 70%, and probably in this one the same. But I am interested in the variation. That means maybe some users of this device can hear 60%, or the speech perception is 60%, others maybe 80%. And in this one, it could be between 74 and 78. So I'm interested on the variation, on the variance of population X and population Y, or device X and device Y. So this is my null hypothesis now. It could be the variance of X equal or larger than the variance of Y, or it could be smaller, or it could be the same. So that's what I am trying to test. So that will depend on the project or the application. And this null hypothesis could be as, instead of variance of X larger than the variance of Y, I can write it the same way as the variance of X divided by the variance of Y larger or equal to 1. And this one will be the variance of X divided by the variance of Y equal or less than 1, and this one just the same. So this is the null hypothesis test of this topic. So first, the statistic parameter is a ratio of two variables, the variance of X and the variance of Y. So this can change, because to estimate the variance of X, I will take a sample from here of size N, and then I will calculate the variance of these samples. And I take here another sample of size M and calculate the variance of Y. So the statistic for me now will be the variance of X divided by the variance of Y of these samples. So this is a variable and this is a variable. And the statistic parameter that I will be using, we call it the F distribution. And the degree of freedom will be the degree of freedom of the numerator. In this case, it will be N minus 1, and let's call it V1. And the degree of freedom of the denominator will be M minus 1, and let's call it V2. So I will be using this statistic parameter to determine the p-value, either to reject the null hypothesis or not. So let's review this F distribution. This variable will have the F distribution with two parameters, or two degrees of freedoms, V1 and V2. The test statistic that we will be using to compare the variance of two populations, we call it F, which has the F distribution of degree of freedom V1 and V2. And F actually consists of two random variables divided by each other, and each one of them has a chi-square distribution. So it will be like Q, random variable with a chi-square distribution of degree of freedom D1, let's say. And another random variable V of chi-square distribution with a degree of freedom D2. In previous slide, we showed if we have a population of normal distribution and we take a sample, then we can calculate the sample variance. Now we created a new random variable U that equal the sample variance times degree of freedom N minus 1 divided by sigma square x, where sigma for our null hypothesis will be set to a fixed value that we compare the variance of the population to that set value. And we can create now another random variable of chi-square distribution for this population that has a normal distribution, population y. And the same thing, we calculate the sample variance. So now we have two random variables with chi-square distribution. Now, if I create a new random variable f that consists of this one divided by degree of freedom. In this case, d1 will be the size of the sample n minus 1 divided by this random variable that has also a chi-square distribution, and v also divided by its degree of freedom, d2, which will be m minus 1, the size of this sample, m minus 1. So I can write u using this definition. So that will be n minus 1 times sx squared divided by d1, which is n minus 1. This is d1. Everything divided by v, which is this value, m minus 1 sy squared divided by the variance here. And also here there is a variance. And divided by d2, which is m minus 1. Now this will cancel this, and I will have sx squared divided by sigma x squared divided, this will cancel this, and I will have here sy squared divided by the variance. For our purpose, for the null hypothesis, we will be comparing these two populations, the variance of x and the variance of y, and we will take a sample and we will calculate the variance of this sample and the variance of this sample. So since our null hypothesis is comparing that the variance of x equal or larger, or equal or less, or equal the variance of y. So for only the null hypothesis test, sigma x squared and sigma y squared will be the same. Then the test will verify, are they the same or not? So then this random variable v1, v2, which has the f distribution, will be just sx squared divided by sy squared. And this is our test statistic that we will be using to set our null hypothesis, that the variance here equal or larger than this, or equal and less or equal. Now, if we want to plot the probability distribution of the random variable f that has f distribution, it will look like this one. And these plots for different degree of freedom, where d1 is the degree of freedom of the variable in the numerator, and d2 is the degree of freedom for the variable in the denominator. The mean, when the samples become very large, the sample size, so the degree of freedom will be very large, then the shape will almost looks like a normal distribution with mean equal 1. Probability density function for the random variable x that has f distribution, this is the equation. But we will never integrate this equation to find the probability that the random variable x will be equal 1 or more or 1 or less, because there is no closed form integral for this function. We usually use software or numerical integration of this function. In this course, we will be using this table. Okay, let's summarize what we have been saying. I have two populations, and I want to compare the variance of population X and the variance of population Y. Then I will take a sample here and calculate the variance of the sample and a sample from this population and calculate the variance of this sample. Now the test statistic F will be S, the variance of the sample here divided by the variance of this sample. And my null hypothesis will be, depend on the application, either the variance of x divided by the variance of y is less than 1, which is the same as the variance of x less than the variance of y, or sx squared less than sy squared. The second possible hypothesis, the variance of x divided by the variance of y is larger than 1, which is the same as the variance of x is larger than variance of y. And the third null hypothesis, variance of x divided by variance of y equal 1, which means both are equal. So let's take an example to demonstrate this hypothesis test for equality of variance. In a series of experiments to determine the absorption rate of certain pesticides into skin, measure the amount of 2 pesticides were applied to several skin specimens. After a time, the amount absorbed in microgram were measured. For pesticide A, the variance of the amount absorbed in 6 specimens was 2.3. So let's draw here A and the sample of size 6, and the sample variance of population A was 2.3. Okay. While for the pesticide B, the variance of the amount absorbed in 10 specimens was 0.6. So let's draw the second population. And we took a sample or tested 10 specimens. And the sample variance was 0.6. Assume that for each pesticide, the amount absorbed are a simple random sample from a normal population. Can we conclude that the variance in the amount absorbed is greater for pesticide A than for pesticide B? Well, the evidence from the sample shows that the variance of the sample A is larger than B. But can this due to a coincidence, due to a randomness in the sample, or is the variance of A is larger than the variance of B because pesticide A is absorbed more in the skin than pesticide B? So we are trying to figure out if this variance A is larger than the variance B. Well, we will set the null hypothesis as follows. H0, the variance of A equal or less even than the variance of B. So we are going against the evidence in our null hypothesis, which is the same as saying SA squared is less than SB squared. And we got 2.3 and 0.6 due to randomness. But let's test it. Let's see if that's the case. So the first step is to calculate the test statistic, which is F of degree of freedom. 6 minus 1, that's 5. 10 minus 1, that's 9. And SA squared divided by SB squared. The variance of A divided by the variance of B. And if we calculate these, that would be 2.3 divided by 0.6 equal 3.83. And if we draw the F distribution for this degree of freedoms, it will come something like this. And 3.83 will be probably somewhere here. So now the task is to calculate this area, which is the p-value. If this area very, very small, then the chance of getting this value from a ratio of 1 is very rare, and it cannot be by coincidence. And we should accept that the variance of A is larger than the variance of B because of the pesticide. And the variance of A here and here, this will be larger than this one because of the chemical and not because of randomness. So now how do we calculate this p-value? We go to the table. We want to find the p-value for 3.8359. So that is degree of freedom of the numerator. This is the degree of freedom of the denominator. So 5 and 9 is here. So we are dealing with this data. So 3.83 is between these two numbers. So 3.48 is somewhere here, and the area here is 0.05. And 6.06 is somewhere here, and this area is 0.01. So for our test statistic that is here, it's this area. So our p-value then will be larger than 0.01, larger than the green area and smaller than the red area, 0.05. So probably it's around 0.04. Calculator or a computer program can give you the exact value. But for our purpose, the p-value is less than 0.05. So let's go back to the problem. The p-value is less than 0.05. So there is strong evidence to reject the null hypothesis at 5% significant level, which means the variance of pesticide A is larger than the variance of pesticide B. Now, it depends on the application. This could be good, this could be bad. Usually, you want the variance to be very small, so the pesticide will be absorbed in the skin from subject to another subject with the same amount and less variation. In this case, pesticide A has more variation. In most cases, we want the variation to be small because we tend to link variation to noise. Okay, this ends this video, and thank you for watching.